Okay. So we are going to talk about the fundamentals of fluid mechanics, and some basic material today, and probably next Tuesday. So I'm going to assume that you are familiar with these topics, right? It is all right if you are not, but you have to let me know. You have to ask questions, right? So I'm going to go as fast as, not very fast, but I'm going to rush through the material. I'm pretty sure you're already familiar with a lot of it. But if not, just stop me, ask questions, right? And we'll go over them in a little more detail. The first thing I want to address today is what is aerodynamics? And I want all of you to answer this question. What do you think aerodynamics is? What is aerodynamics for you, essentially? Yes.
Airflow, downforce, lift.
Airflow,
Drag.
downforce, lift, drag. Okay, what was your name again? Gavin. Okay. What else?
How fluid flows over a surface.
How fluid flow over a surface. Anyone else? What was your name? Michael. Yeah. So essentially, as Michael and Gavin mentioned, we are mainly dealing with the flow of air. In aerodynamics, we are talking about the dynamics of air flow, right? So we want to characterize, we want to understand the motion of air, specifically on a surface, right? So it is not just a random motion of air in the atmosphere. It is the motion of air on a surface and how it interacts with that surface. And eventually, we want to characterize the forces that is exerted by air on that surface. That surface can be an airplane wing, it can be a fuselage, it can be anything that is flying, right? So that is the goal here. And whatever we do in this course is eventually going to help us quantify the forces that are being applied, that are being exerted on an airplane. In this course, we are mostly concerned with external aerodynamic. In general, we have two types of aerodynamics: internal aerodynamics and external aerodynamics. External aerodynamics talks about the flow of air on plates. It can be a flat plate, it can be a curved plate. A curved plate, meaning it can be a wing or fuselage or whatever, right? Internal aerodynamics talks about the flow of air inside of the ducts. Can any of you give me an example of internal aerodynamics? Yes. Air conditioning. So literally flow of air in ducts, right? That is a correct example. What else? Can you speak on? Jet engines, exactly. So a more common type of internal aerodynamics is jet engine analysis and design, right? If you're an aerospace engineer, you don't really do air conditioning design, but air conditioning is aerodynamic, internal aerodynamics. That's true. Okay. So, but in this course, we are mostly focused on flow of air on things, on a plane, essentially, different parts of a plane. Okay, so we understand aerodynamics is the flow of air. Aerodynamics is part of the general fluid dynamics or fluid mechanics analysis. It also has other parts like gas dynamics or hydrodynamics. Now, from their names, you can say gas dynamics talks about the movement of any gas, not just air, on things or inside things. Hydrodynamics talks about movement of water on things or inside things, right? But we are mostly concerned with aerodynamics. If you were to analyze the motion of or movement of a plane in another planet, then your analysis should be gas dynamics. It should be a little more general than aerodynamics, right? But on Earth, we are mostly dealing with movement of air. Let me ask you, a side question. What branch of fluid mechanics are we going to deal with in a space? Not on a planet, not in an atmosphere, in general vacuum of a space. Because on Earth, we said if you're a plane flying, you are concerned with aerodynamics. In oceans, hydrodynamics, yes.
Like streamlines and three-dimensional flow.
I mean, streamlines and three-dimensional flows can be any type of fluid mechanics, right? Because we have streamlines in aerodynamics, in hydrodynamics, or in gas dynamics. What are streamlines?
It's how the fluid or gas or air flows off of the surface.
Yes, exactly. There's a specific definition which we'll get to later. Anyone else? So what branch of fluid mechanics discusses the movement of objects in a space?
If it's a vacuum, there shouldn't be anything to control.
Exactly. There is no fluid mechanics in a space because there is no fluids in a space. There is no atmosphere. It's vacuum, right? So that was a trick question. Okay, so a study of aerodynamics. What should we know? First of all, the first thing we need to know in a study of aerodynamics are the dominant or most important parameters that we are going to deal with. Important parameters. As I said, you are essentially going to find the forces acting on your plane, lift, drag, mostly in aerodynamic analysis. But in order to find these forces, we have to start somewhere, right? And that somewhere is by identifying the important parameters that we need to deal with. We need to start from, right? What are those important parameters? Can we have any guesses? Yes. Temperature. What else? Pressure. What else? Velocity. Velocity of your plane or velocity of air. What else?
Density.
Density, exactly. Thank you.
Mass.
We are dealing with density, so density, mass. Density is the specific mass, right? Volumetric mass. Shape of the object is very important, but the velocity profile is going to include the shape. Is going to take into. Is going to take the shape of the object into account. Yeah.
Would surface area go along with that, or would that be?
Yes. Yes. Surface area.
Angle of attack.
Angle of attack again. Velocity profile.
Viscosity.
Viscosity. Viscosity is another important parameter that we need to think, especially considering the fact that this is a fluid mechanics analysis. So viscosity is very important, is very prominent here in any type of fluid mechanics analysis, right? We don't really deal with viscosity in solids. We only deal with viscosity in fluids. But velocity, pressure, all of those other things are also available in solid analysis. You have to keep in mind that we have dynamic viscosity, which is mu, and we have kinematic viscosity, which is the symbol for which is nu. So nu, this is how it's pronounced, and this is mu. How are these two related? Does anyone know? How is kinematic viscosity related to dynamic viscosity?
This might be wrong, but you multiply one of them by the density.
You essentially, yes, exactly. So kinematic viscosity is your dynamic viscosity divided by density. Right, that's how it is defined. There is one more parameter that is very important in aerodynamics, specifically in aerodynamics, right? And that is the speed of sound, A. The speed of sound is very important here. That's how we actually can figure out whether a flow is supersonic, subsonic, or sonic flow, right? Right? So the speed of sound is very important. Most of our analysis, or I should say all of our analysis here, is with subsonic flows, incompressible subsonic flows. So very low speed flights. But you should understand that the speed of sound is a very important parameter when it comes to aerodynamics. Let's circle back to viscosity. I said viscosity is very important in fluid mechanics, general area of fluid mechanics. Is there anyone who can elaborate on this, can tell me why? Why is this specifically important? Or let me back up a little bit. What is a fluid in general? What is the general definition for a fluid?
It's where when particles are loosely bound together, but not enough, rigid enough to form a solid.
Yeah, that's a correct answer from a molecular perspective, right? But from a mechanical engineering perspective, how would you define a fluid? Yes. Something that flows. Okay. Can you make it a little more scientific?
Conforms to the boundary.
It takes the shape of a container. Okay. What else? Think of a shear stress resistance. How does a fluid react when a shear stress is applied to it? Think of two plates here. Right? Let's say I'm pulling this plate with a velocity u, and this plate is stationary. And we have fluid in between. What will happen? Let's say we have solid in between. What will happen here? It's just a block of solid. What will happen if I just pull one side of it? But let's say before fracture, what will happen there? It will deform a little bit, right? It may be an elastic deformation or plastic, right?
For the solid or for the gas?
Pardon me?
Wait, you're talking about for the solid or for the gas? Right?
This is let's say this is a block of solid,
Oh, okay, my bad.
a solid block. So if I pull on here, it will change its shape a little bit, right? A solid. If I remove this force, it will probably go back to the original station, elastic deformation. Even with the plastic deformation, it will go back a little bit, right? And we are not talking about fracture or anything. Well, what if between two plates we have a liquid? And I'm pulling here. What will happen?
The top part of the liquid where it will gain the speed of the top plate, and the bottom stays stationary.
Stationary. And what will happen if I remove the?
It won't go back.
Well, it won't go back. It will continue flowing, right? So a fluid cannot resist the shear stress. But the normal stress, nothing happens to it. Nothing happens to a liquid specifically, right? A gas is also that cannot resist the normal stress as well, right? But in general, fluids cannot resist shear stress. Now, how can we quantify the shear stress in a fluid? Does anybody remember? It is related to the viscosity, which directly talk about its resistance, the fluid's resistance to shear stress, right? And the gradient of velocity, x direction velocity specifically, if this is x and y, in the y direction. So changes of velocity, this velocity, in this direction. So essentially, for this specific case, velocity at this location is this much, small. It will grow bigger, bigger, and bigger until it gets to this plate's velocity. So we have some sort of a change. Does that make sense? So in a fluid, shear stress is related to viscosity and the gradient of velocity. And as I said, in aerodynamics, we are mostly focused on finding out the forces exerted by a fluid on an object. So understanding shear stress and understanding viscosity is very important here, right? We have models that really don't use viscosity. We have assumptions that don't use viscosity at all, but we'll get to those later. But in general, viscosity is a very important parameter. One question we need to answer before moving on about viscosity is, how does viscosity change? How does it change in general? Is viscosity constant? Or is it a function of other parameters? We had one no. Who said no? No one?
It often decreases when heated.
Viscosity decreases when heated. Is it true for any type of? Let's not get into that. That's a different discussion. Yeah, it changes. Let's say in general it changes with temperature, right? And there are different rules. There are different laws that actually tell us how viscosity changes with temperature, right? One of these laws that I have included in my lecture notes is a Sutherland's law. Which tells us that viscosity is a function of temperature to the power 1.5 for air. This only applies to air. For or gases and regular gases and liquids. Okay. A and B are constant that are going to be given to you. But in most of our analysis, we are going to assume viscosity is constant, mainly because our operating temperature doesn't change that much. Okay? Does it make sense? Any questions so far? No. So let's move on. Let's go back to the original parameters we had. We had pressure, we had viscosity, we had fluid velocity, we had the what else? We had a lot of other parameters. And we want to see how are these parameters related to each other. right? To essentially be able to analyze the fluid flow, the motion of air on an object. Okay? Let me ask you this. We all have passed fluid mechanics, right? Fluid mechanics or aerodynamics. Yes? Okay. What are the governing equations that govern the movements of fluids? What are the principal? Bernoulli is one of them, right? But there are a lot of limitations with Bernoulli, right? Do we know what are the limitations of Bernoulli?
Can only be used with laminar flow.
For laminar, incompressible flow specific. There are like 4 specific assumptions when it comes to Bernoulli. What are the more general? You should just. I just want the names. I don't want the equations. The more general fluid flow equations. Anyone? So there are 3 specifically. Conservation of mass. And we are going to go over these later. So don't worry if you don't remember them. Or I know there are some classes that really don't go over this. So don't worry if they haven't gone over this. The momentum equation, which is essentially Newton's second law applied to fluid, so momentum equation, as well as the energy equation. Okay, are we familiar with these 3 equations, the governing equations? Have you at least heard the names? Yes, okay. So this is how we relate all of these parameters to each other with these general equations. Of course, for specific conditions like incompressible laminar flows, we can use Bernoulli's equation or a lot of other simplifications for this equation. But we have the general equations that we are going to go over hopefully in the next lecture. But what we want to do here is to see if there is any other way of looking at things that is going to make things simple for us, but is also general enough. Let's think about it. So instead of using these partial differential equations, we want to come up with some things that relate these parameters to each other, and is going to give us a very good understanding of the fluid flow. I'm specifically talking about the dimensionless parameters. So dimensionless parameters are parameters that are going to give us a relationship between the main parameters, the primary parameters we have, and are going to help us characterize the fluid flow or airflow. And since they are dimensionless, we can actually use those numbers, those parameters everywhere. Are we familiar with dimensionless parameters? Yes. Can you give me an example?
Reynolds number.
Reynolds number. Reynolds number in fluid mechanics is the most important dimensionless parameter. How do we calculate the Reynolds number? Do you remember?
Not off the top of my head.
No problem. It's rho multiplied by your velocity multiplied by length divided by viscosity. Or we can actually give it in terms of kinematic viscosity. So velocity multiplied by length divided by kinematic viscosity, nu. You just have to keep in mind that this L is a characteristic length. So depending on the condition, it may be just your plate's length, or it may be any other length that you choose. You just have to be consistent. So Reynolds number. There are other dimensionless parameters that are going to help us characterize and understand the fluid flow. Let's just start with the Reynolds number. Let me And I want you to answer this. What does this Reynolds number signify? Or what does it, let's see, what does it measure? That's a better way to put it. What does Reynolds number show us, essentially?
How turbulent the flow is.
How turbulent your flow is. So essentially, what was your name?
Richard.
Richard is definitely correct. Reynolds number is going to, there is a specific number or a specific range of Reynolds number that are going to tell us whether a flow is laminar or turbulent. And Reynolds number itself is the ratio of inertial forces versus viscous forces. If your viscous forces are dominant, meaning that small Reynolds numbers, viscous forces is dominant. Then you have laminar flow, which is, I always call laminar flow an ordered flow. It is very orderly. There is no mixing happening. There is no chaos, right? While for larger Reynolds number, inertial forces are going to be dominant. And we are going to have turbulent flow. But how is this going to help us understand anything about the flow? It's just a number, right? And in order to find this number, we have to have all the other parameters. We have to have the density, we have to have the velocity, length, viscosity, right? If we already have those, why do we even need the Reynolds number, right? This is where flow similarity comes into play. What does flow similarity tell us? Flow similarity specifically is telling us, since Reynolds number and other dimensionless parameters that we are going to talk about later are dimensionless, if we measure the velocity on a small scale, in a wind tunnel, for example, on a small scale plane, right? If we measure the velocity, we can measure it. It's an experimental setting, we can measure anything, right? If we measure them and if we calculate the Reynolds number, we can actually have the exact same properties for a similar Reynolds number in a real flight. Let's say you have the density, velocity, viscosity, and length in a wind tunnel. You calculate the Reynolds number. But for a real flight, you only have the density and length and viscosity, and you want to know the velocity. What you know is that these two flights have the same Reynolds number, because the Reynolds number is dimensionless. It's not a function of your dimension. You can easily find the velocity based on the experimental data. Does that make sense? So dimensionless numbers are very helpful, but there is one caveat here. You need to have some experimental data present to be able to do the flow similarity analysis. And we're going to do some flow similarity. We're going to solve some examples with flow similarity. Some flow similarity problems later, so it will give you a better understanding of what flow similarity is. And this lecture, we are mainly focused on these dimensionless parameters. Next lecture, we are going to focus on the main governing equations, the conservation of mass, a momentum equation, and the energy equation. Okay, so let's just let's see if there are any other dimensionless parameters that may be important in aerodynamics. Can we think of anything else? Mach number, right? Exactly, the most important one. How do we calculate the Mach number? Velocity over the speed of sound. Exactly. The speed of sound is meters per second. Velocity, flight velocity, is also meters per second. So Mach number is going to be another important dimensionless parameter. Dimensionless parameter. One thing I need to address before moving forward is the speed of sound. How do we measure the speed of sound? Is there anyone in class who has a clue or has an idea? You don't have to be correct. You just have to have. Yes.
You have to detect sound at a known distance and record the time it takes to pass it.
So what you're saying is that you essentially have to have a sensor, right? Two sensors. One that is going to emit, like create a pressure wave, and one sensor that is going to detect that pressure wave, right? Then you can measure the speed of sound. Exactly, that's true. Is there any other way? Can you think of any other way? Let's say you are in a flight. You don't know the speed of sound there, right? And you don't have the ability to put in two sensors out of the window, right?
When the shock wave comes?
Shock. I don't see how this is related.
Once the vehicle reaches the sound, the speed.
It is not experimental. Let me.
Oh.
So this is an analytical method. Do we have any? Did you want to say? I saw a hand over here. No.
Same idea as him.
Okay. I'm not talking about as experimental method of measuring speed of sound. There is an equation. A speed of sound is specifically related to your medium, right? And also the temperature of that medium. So we can actually have an equation that is going to help us calculate the speed of sound. It is related to a square root of gamma r t. Okay, have you seen this before? Temperature. You know what temperature is? Temperature of your thing. What is R?
Gas constant.
The gas constant. The specific gas constant here, not the universal one. Do we know what is the gas constant for air? You don't remember?
About 287.
287. Exactly. If you are an aerospace engineer, you have been dealing with this number a lot, so you probably remember this. What about gamma? What is gamma here? In some textbook, they call it K. Yes.
The ratio of the specific heats for constant pressure and constant volume.
Exactly. So gamma is the ratio of a specific heat, Cp, C of P and C of V. So constant volume of specific heat, constant pressure of specific heat divided by constant volume of specific heat. And we usually use the number 1.4 for air. This, of course, changes with temperature. Yeah, pardon?
The cold air standard, I believe.
That's right. But we usually use it. We always use 1.4 in this course. Okay. Okay. So we understand the Mach number. We understand the Reynolds number. We know how to calculate the speed of sound, which essentially means that if you have the flight velocity, you should be able to calculate the Mach number. Or if you have the Mach number, you should be able to calculate the flight velocity. Okay, what are the other dimensionless parameters that are important here? We haven't talked about the most important dimensionless parameters yet. And those are the force coefficients. So in order to understand the force coefficients here, we need to understand the forces that are applied, that are exerted on an airplane, right? What are the forces that are exerted on an airplane? Let's say this is I don't think this can fly, but just accept them. What are the forces that are applied? The gravitational force, weight, right? But this is not a force exerted on the plane by air, right? This is just a gravitational force. What else do we have? Drag. Drag is a force that is exerted by air. Lift also is a force that is exerted by air. And we also, yes,
Applied force for.
thrust. Huh? Exactly. But thrust is also generated by the jet engine. So it is not a force that is exerted on air. In this course, we are going to focus on these two. So another dimensionless parameter are the force coefficients, specifically drag and lift coefficient, which we use C of L and C of D for, to specify these two. But we'll get to their calculation later. We'll get to their equation and calculation later. Let's talk about the forces themselves. Our goal in aerodynamics is to maximize lift to drag ratio. So this ratio, lift to drag ratio, is a very important ratio, and we want to maximize it. And let's see. Let's actually talk about some of the nomenclature here. We have an airfoil. What is an airfoil? Is there anyone in class who can give me a definition of an airfoil?
It's a shape that controls the airflow around it in a way that would create less.
So, what is the difference between an airfoil and a wing then?
I'm sorry, what?
A wing, like a regular plane wing. Any one of you can jump in. This is a discussion, so you can jump.
An airfoil is a cross-section view of the wing.
So that's the difference, right? It is a two-dimensional thing. So it is essentially a cross-section of a wing. Of airfoil. And we have different names for different parts of airfoil. The first thing you need to know here is the chord of an airfoil. Where should I draw them? Where is the chord? Chord line.
Through the center of the.
It connects through. It is not necessarily through the. What do you mean by through the center?
If you track the curvature, it's going to be in between the top and the bottom.
That is the camber line. That's why I asked it. That is not the chord line. So a chord line is the closest distance between the leading edge and the trailing edge. You may want to know what are leading edge and trailing edges. Leading edge is the first part of the airfoil that sees the air, the incoming air, right? Trailing edge is the last part of the airfoil that sees the outgoing air, essentially. So a straight line that connects these two is called a chord line. And its length, which we usually show by C, is called a chord. But the line that has the same distance from the top and bottom of the airfoil, same distance, is called a camber line or a mean camber line. Okay? And the distance between the two is called the camber. Thickness of the airfoil is, of course, the distance between the upper surface and the lower surface. Is the thickness. We know what thickness is, hopefully. And there is one important parameter that we need to discuss here, and that is the angle of attack. Angle of attack is the angle between the free stream, let's call it streamlines. streamlines of the flow, and the extension of the chord line. So if you extend the chord line, the angle at which it cuts the incoming flow is called the angle of attack, or alpha.
Is the camber the curved line or the largest distance from the chord to the
Camber is the distance. Max camber is the largest. So let me try to, this one didn't have that much of a curvature. Let me try with this type of airfoil. So for this type of airfoil, this is going to be your chord line, right? But this is the camber, the mean camber line. This is camber. This camber can change throughout the airfoil, right? We have actually a maximum camber, and a minimum camber is always 0. Let me ask you this before moving forward. Let's say this is a symmetric airfoil, meaning that there is a symmetry axis in the middle. What is the camber of this airfoil? The camber of this airfoil is 0, exactly, because the camber line is on top of the chord line. It's a symmetrical airfoil. Does this make sense? Okay. So let's move on to forces. Let's go back to forces again.
Can you show the angle of attack one more time?
Here it is. Let's go back to the forces. Let's say we have this airfoil, and I have this question for you. How can nature, in this case air, exert force on an object? Or how does it, not how can, how does it exert force on an object? How does it talk to an object? What are the different forces that air can exert on an object? Different type of forces.
Pressure differences?
A pressure difference is not something that you exert on an object, right? Pressure difference is between two locations of the flow. But pressure itself is one type of force, right? A normal force, right? So pressure force. What else? Shear force. Exactly. These are the only two types. So a force is exerted on an object either through shear or through pressure. Does it make sense? This pressure and shear can change throughout this body, but we will always have pressure and shear present. So I mean, one of them can be 0, but if you have a fluid motion, you will have either pressure or shear present at any part of your object. So we can combine all of these together to a resultant force R and also a resultant moment M, right? Why do we have the resultant moment? I assume you understand why do we have the resultant force. We just combine all of the forces. These are vectors. We just add all of the vectors together, a resultant force, right? And in this is a pressure distribution, so we have to take the integral. Right? We have to integrate, right? It's just it is not a simple addition. But why do we have the moment? Why does it have to be a resultant force and a moment? Yes.
Because the point that you drew on the airfoil is not the point that's being exerted on by the force.
Exactly. So we have a force exerted here, which is going to cause a moment here. And if you want to combine all of the forces at a specific point, you have to include the moment that is going to be exerted on that specific point. So we are going to have a resultant force and a resultant moment. Any questions so far? Okay. So let's move on. We can have two different type of analysis when it comes to analyzing the forces. We can actually find the components of force on the chord line. So let's go back to this force, the R force. And as you know, we are very obsessed with the components of a force because it is going to make it easier for us to do a force balance, right? If I have the different components of the force, I can write sigma f of x equals to 0, sigma f of y equals to 0, then it will be simpler, right? It's a vector, right? So when it comes to finding the projections and components, we are going to have two perspectives. One is by setting the chord line as your base, as your axis, essentially, as one of your axes. If you do that, then we are going to call these forces axial force. We're going to use A. And this force we are going to call normal force. Okay? Or a more common type of analysis here is to use your flight path, essentially, as your base. Let's say we have this angle of attack alpha. Let me change colors here. What did I change? Let's say this is the path your flight is taking. We can use this as the base axis. If we do that, then we are going to call the components drag, and I'm just choosing random colors, and lift. So it is very important to keep in mind. Drag and lift are normal and tangent to the flight path. Axial and normal force are normal and tangent, or tangent and normal, to the chord line. What will happen to this if angle of attack is 0? What will happen to these components if angle of attack is 0? If angle of attack is 0, then chord line is going to coincide with not with drag, with flight path, right? Which essentially means that your lift is going to be equal to your normal force, and your drag is going to be equal to your axial force. Does it make sense? Very simple. But in general, we can actually, there is a trig relationship between the lift and drag. These are all vectors. We know these angles. This is the angle of attack. If you do the trig analysis, you will find this angle is just the angle of attack, right? So we can find the relationship between lift and drag as a between lift and the other forces, normal and axial force, as a function of angle of attack. Lift is going to be equal to n multiplied by cosine of angle of attack minus a multiplied by sine of angle of attack. And drag is going to be equal to n sine of alpha plus a cosine of alpha. Does this make sense? Okay. By doing this, we are essentially going to make it a little easier to relate lift and drag to pressure and shear force, because then all of the components are going to lie on your object, not on the flight path, right? Yes?
You said A was also the variable for speed of sound. I'm guessing we're never going to see both of them together in an equation. Because that's a different A, right? That's not.
This?
Yeah.
So a speed of sound is a small a.
Oh, it's a small. Okay. I didn't know.
Yeah. Let me actually, I should have mentioned this. Capital A, or big letter A, is the axial force. and alpha is the angle of attack. Okay? So we're gonna use N and A and find the relationship with the shear and pressure. And then we're gonna use this equation, these equations, and relate shear and pressure at every point to lift and drag. Lift and drag are more common, as you all have heard. So let's actually go back to this airfoil. Let's look at this point A. At this point A, we are going to have one component of this this normal force per unit area. So we haven't combined all of the forces together, right? At one location yet. If you are looking at only one point, you are essentially you are looking at a force per unit area. Does this make sense? It is the same as pressure. We don't really have force at one point, right? We have pressure at one specific point, right? And pressure is force per unit area. Okay. And we are going to show this force per unit area by N double prime. And this U stands for upper surface. And again, N has to be perpendicular to the chord length. And axial force, we're going to have the same thing for axial force. Which is axial to the chord line. Which is tangential to the chord line. What is the direction of pressure and shear here at this specific location? Pressure is always normal to your surface. So this will be the direction of, maybe use a different color, direction of pressure, right? What about shear? Tangent to the surface. And we are going to call the angle between these theta, which is a function of the shape of the airfoil. So if you have the equation of the line for that airfoil, you essentially have theta. Does that make sense? Okay, let's go back to color black. So again, there's a trig relationship here for both forces. N double prime U is negative pu cosine of theta minus tau of U sine of theta. And A double prime U is negative pu sine of theta plus tau of U cosine of theta. Okay. And how should we convert this to the total force, N or A? How can we do this? This is force per unit area at each location, right? How can we convert force per unit area to force? Multiplied by area, but it's not that simple. Why? Because this force, this pressure and shear is going to change at different locations. So we have to integrate. So your total force N, normal force, is going to be negative from the leading edge to the trailing edge, pu cosine of theta plus tau of U sine of theta dA plus the integral of leading edge to trailing edge, PL, and this L stands for the pressure on the lower surface, minus tau of L. So we can do the exact same analysis for the lower surface, dA. And your actual force is going to be integral of leading edge to trailing edge, negative pu sine of theta plus tau of u cosine of theta dA plus leading edge to trailing edge PL sine of theta tau of L cosine of theta dA. So element of area. You have to keep in mind that this is talking about a wing, a three-dimensional wing, not an airfoil. Airfoil is a two-dimensional thing, right? And dA is a small element of area here. But if we are dealing with an airfoil, we are going to assume a unit depth for the wing, right? The imaginary wing. So we are going to assume that this depth is 1. And your dA is going to look like this element of area, which is going to be a small element of this length we are going to call ds. S stands for the path. I mean, this shows the path, essentially. The path you are taking on this airfoil, right? And this small element of that path is called d of s. Okay? So your area, or dA, is ds in meters multiplied by 1 in meters. This is meters squared. So let's simplify the equations. ds multiplied by 1, ds multiplied by 1, and this ds of the upper surface. Just have to keep in mind that we have different equations for upper and lower surface. Multiplied by 1. Something that you have to keep in mind that this is not just a number. This is a dimensioned number. There's a dimension here. So we cannot just remove it. We have to move it to the other side. If we move this 1 to the other side, the unit here is going to be newtons per meter, right? It is not going to be newtons anymore. So we are not talking about the total force. We are talking about the force per unit length. Not per unit area anymore, per unit length. Because we assume the unit depth for the system. Okay, and we are going to show this force per unit length with prime. Whenever you saw prime, N prime, L prime, D prime, it means that we are talking about force on an airfoil. Force per unit length, essentially. Does this make sense? Okay. Yes. Whenever you see double prime in this, when it relates to forces. Whenever you see double prime, we are talking about the force per unit area. Whenever you see just single prime, it's force per unit length. So double prime is talking about the force that is acting on a point, right? Single prime, a force that is acting on a line, like an airfoil, a two-dimensional thing. And no prime is talking about the force that is acting on a plane. Okay? Does this make sense? So let's move on. We can actually find the moment around the leading edge as well. I'm just going to give you the equation for this moment. But it's essentially very similar to the equations we have. Just have to include a distance from the leading edge. So if you are talking about the normal force and actual force, normal force acts on this distance, so x. Actual force acts on this distance, y, right? Is we're talking moments, right? Moment force multiplied by the distance. So where were we? Yeah. So this moment, this is multiplied by x minus pu sine of theta cosine of theta y ds on the upper surface plus another integral from leading edge to trailing edge pl cosine of theta plus tau of L sine of theta x plus PL sine of theta, this is PL, plus tau of, this should be tau of L. So there's a typo in the notes. This should be tau of L. Cosine of theta y ds L. These are very lengthy equations, but we don't really use these equations that much. We always simplify them because the cases that we are going to work on are much more simpler than a real airfoil. It is usually a flat plate or something like that. The cases that you have to do an analysis on. So don't be scared by the form of these equations. You can simplify. We will going to solve an example if we have enough time. Let's actually go and solve that example and come back. This example is also in your notes. So we have this flat plate. And we are given the pressure distribution on the top surface of the flat plate as a constant number C1 and pressure distribution on the lower side of the plate, which is just C2. The chord length is C, and as you can see here, P on the lower surface is larger than P on the upper surface. Okay. We have an angle of attack, alpha, and Mach number is larger than 1. And we'll get to those. We are asked to find M prime of LE, so moment per unit length. And we are also asked to find the normal force here per unit length. Let's actually make it a pop-up quiz for your attendance. I did pop-up quizzes in all of my classes today. So let's make it a pop quiz, attendance quiz. I'm sure you are familiar with the attendance quizzes, right? So essentially, I'm going to ask you to solve a problem. You don't need to have the correct solution. You just have to put an effort into it. And then you have to submit your quiz. So let's find the M prime and L prime. M prime over the leading edge, and N prime in general. And we are to ignore the shear stress. So whenever you see tau, that goes to 0. See, already Much simpler. Before you start, and don't forget, if you don't have, I really don't have extra papers with me right now, so if you don't have a paper, just borrow one from your classmates. Make sure to submit your quizzes because that's the only way I know you're in class and you'll get the points, right? Before you start, let me ask you this one question. What can you say about the actual force per unit length? And this is for this specific problem. Zero. Why is this zero?
Forces all normal to the chord line.
Forces are all normal to the chord line. Exactly. So your theta here is always zero, right? There is no curvature on your airfoil. So which means the actual force just zero. But that doesn't mean drag is zero. Just the actual force. So if you are dealing with a flat plate, your actual force is zero. So find the n prime and m prime. I see some of you have your computers in front of you. The answer to the quiz is in the lecture notes. Don't look at the answer, because you are not graded on your answers. I just want to make sure that you work on it. Right? This is not something that you are graded on, so just work on it a little bit. This is pretty simple. One thing that I need to add here is your coordinate system. So we're going to assume x and y are in the direction of your chord length, okay? Which essentially means that your ds is dx. Does this make sense? Because your path is in the x direction. Does this make sense? Okay, so let's see. Do you have anyone who has any ideas how to solve this? Okay, let's solve this together. Let's look at this n prime. What can you say? How can we simplify this? We have the equation in front of us. How can we simplify this?
Eliminate the terms with the tangential force. It's equal to 0.
Exactly. So the terms that have tau are going to 0. What can we say about the rest of it? Is there any other simplifications we can do here?
Since theta is 0, the sine or cosine of theta would also be 0.
Cosine of 0 is 1. Make sure you don't make that mistake, because then everything goes to 0, right? And what can we say about ds?
ds
dx, right? On the lower and upper surface, they are essentially the same thing. It's a flat plate. So dx. So for our problem, n prime is going to be the negative from leading edge is x0, right? Because everything is changing in the x direction. In this case, leading edge is x0, and trailing edge is x equals to c, right? We don't have any variations in the y direction. So leading edge is here, which is x equals to 0. Trailing edge, x equals to c. And pu, right, based on this equation, pu is the only term standing in the first part of it, minus, there's a minus sign, right? Plus, actually. Plus PL. It should be minus. It should be, okay. So this theta, that's a very important point that I made a mistake here myself. So this theta on the lower surface is not 0. That's something that you have to keep in mind. This is 180 because we are talking about the lower surface here, right? So we have moved around that. Does it make sense? So this is -1. Okay, so pu minus pl dx. And we can bring in this negative sign in the integral. It's going to give us PL minus PU dx. Can we take this integral? Pressures don't change, so the only variable here is dx, and integral of dx is, what is the integral of dx? X. So your force is PL minus PU multiplied by x. X goes from 0 to c. X is equals to 0 will make it 0. X is equals to c will make it c. This is going to be your normal force. What about the moment? Go back to moment here. Moment equation. Here, this is ds, dx. This is also dx. These taus are 0, right? And then we have sine of theta is 0. Cosine of theta is 1 on the upper surface. Cosine of theta is -1 here, right? And sine of theta is 0 here. Just have to make sure that you have the correct signs in the equation. You eventually are going to end up, if you do the simplifications, you are again going to end up to 0 to c, pu minus pl, x dx. What is the integral of x dx? Because p doesn't change, that's a number. What is the integral of x dx? X squared over 2. It goes from 0 to c. X0 is 0. So you're going to have pu minus pl, c squared over 2. This is going to be your moment. It's actually pl minus pu based on the solution I have. Okay, so we have the n and we have the m. And we are at 539. Let's see, there is one more thing that I wanted to mention. It won't be more than 1 minute. So what is the center of pressure? Is there anyone who can tell me? Do we remember center of pressure from fluid mechanics? Have we heard about center of pressure in fluid mechanics? Yes or no? Yes. Do we remember? Yes or no? Do we remember what it was?
The point where the moment is 0.
Exactly. Center of pressure is a point where moment is 0. What does this mean? This essentially means that we said we had these distributions of pressure and shear here. When you combine these together, you can find a specific point at which all of these moments created by this pressure and shear forces cancel each other. That specific force, where moments is 0, is called the center of pressure. And it's, of course, very beneficial to us to use the center of pressure as the point we want to put our forces on, because we don't have to deal with moments anymore, right? So let's go back to this example. How can we find, and that's the last thing we are going to discuss here, how can we find the center of pressure for this example? Essentially, we already have, where did I go? We already have the moment caused by all of these forces, right? That moment is not equal to 0. But the idea is that moment should be equal to the moment that is generated by the forces. That is the moment at the leading edge, right? So if we put this force, we have to find the location. We have to find a specific location on this where the moment generated by the resultant normal force is actually equal to the moment at the leading edge. Does this make sense? Then that is the location of center of pressure. And here we only have the normal force, which means that m dot at the leading edge has to be equal to x of center of pressure multiplied by n dot. N dot is your total force, right? M dot at the leading edge is the moments at the leading edge. And the center of pressure is a distance from the leading edge. So we essentially have to find the location where that force is going to generate the same moments, right? So we have already calculated this n prime. We have already calculated this m prime. And if you plug it in, the location of center of pressure from the leading edge, the distance from the leading edge, is going to be equal to PL minus PU multiplied by C squared over 2 divided by PL minus PU multiplied by C. Which means that so what does it simplify to? C over 2. So this tells you for a flat plate, the center of pressure is at the center of that flat plate. Okay, so let's just stop here. We are already